In section 3.5, we'll be solving logarithmic and exponential equations. The first 2 pages will be looking at the logarithmic equations, and on page 3 and 4, we will be solving exponential equations. You will see on page 5, I created about 5 problems that I want you to try. Here we go. The 3.5 problems, I want you to just work them out on a separate sheet of paper, show work each steps, and submit them on Canvas for me for 3.5 problems. These 5 are the ones that were on exam 3 for in the fall semester. So I want you to be able to do something like this. Just want to mention that I want you to give both the exact value and the approximate solution, and we'll talk about what I mean by that as we go over the first 4 pages. So this can be found on Canvas. I'll call it 3.5 problem to submit. I did also type it here, but make sure to show work and the exact solution and the approximate decimal solution to 4 decimal places when you submit these, okay? All right, so let's first, probably gonna go over the logarithmic equations first on the first 2 pages, and then I'll stop and I will come back and go over the exponential equations on a separate video, okay? All right, let's solve some log equations. So I got some steps listed here for you. So step 1, given a logarithmic equation, we're going to isolate the log on one side of the equation. So if you have log on both sides, you want to make sure that we put all these log expressions on the same side. I usually put them on the left side. Step 2, if you need to, use the log properties that we went over in 3.4. We're just going to combine them and write them as a single log. And then step 3 is going to be important, where you will convert these equations in exponential form, okay? So when you're solving log equations, you will have to convert those into exponential form. And the other way around, when you're solving the exponential form, you will have to bring in the log expression. All right, and step 4, once you rewrite it in exponential form, you're just going to solve for the variable like x or y. And then lastly, we want to check the solution. We're going to check the solution. So there's a 5-step process, but some are going to be a little bit simpler, like the first example. Let's go over number 1 and 2 on solving an equation of the form that's already in log base b of a equals c. So as you can see, number 1, let me zoom in on number 1 right here. It's already a log expression isolated on the left side, right? There's only log expression on the left side. There's no log on the right side of the equation. So first step, second step is done because it's already a single log right there. So what we're going to do first is we're going to rewrite this, rewrite in exponential form. Okay, so the question is, what is the base? What's the base here? The base is 64. So you'll say 64 raised to the what power? 1/2 power, and that equals the argument of x. Now we actually solved it. We solved this equation in a single step. X is 64 raised to the 1/2 power. And 64 raised to the 1/2 power, taking a 1/2 power is the same thing as taking a square root. So x is equal to 8. Now we want to check the answer. So if you want to check the answer, what you can do is you can plug in log base 64 of 8 and see if that really comes out to be half. So we can use our calculator to type in this left side and see if that comes out to be 1/2. Let's do that together. So let me go and type in log base 8. Oh gosh, guys, I forgot what I was writing just now. Log base 64 and 8. Log base 64 and 8. Log base, I'm just going to retype everything. 64 in the base and then 8 as the argument. If I hit enter, I got 0.5. And 0.5 is 1/2, so we got the answer right. So sometimes when you check the answer, you will see that, oh, the answer doesn't really make sense. So that's why I kind of want you to check your solution when you're done, because you may get extraneous solutions, and we'll talk more about them. But it's a good habit of always checking your solution after you get the x value or y value. Just plug it back in and see if that's really true. Let's try another one where, again, this one, if you take a look, it's already a log expression isolated on the left side, and we only have single log. So we're going to start by just simply rewriting this. Rewrite this in exponential form. And this is what you guys really practiced on that quizzes for me in section 3.2. So I know you can rewrite this. So let's go ahead and rewrite this. What is the base? Base is 9. And the exponent, the power is -2. And that equals x. Now we solved it. We got the answer. That's the exact answer, but we can simplify this. What does it mean? 9 to the -2nd power. Using the exponent rule, we know that's the same thing as 1 over 9 raised to the +2nd power. So that's the same thing as 1 over 81. So let's check the answer. It's just a good habit. Let's check. Check and see if log base 9 of 1 over 81 is really -2. Okay, we're going to check that, okay? 9 and 1 over 89. So I will go log base 9 and 1 over 81. If I hit enter, I get to -2. So just like that, I want you to kind of always check your solution. Because later on, you'll see some things, some of these equations that will have extraneous solution, okay? Okay, so those I consider to be the easiest problems, where all you need to do is just rewrite the equation that's currently in logarithmic form to exponential form. But sometimes, step 2, the type 2 that I got right here for you, these are going to be the multi-step. So we'll try these first, and we're going to round the answers to the nearest 100th, okay? All right, let's look at number 1 here together. Now, what we're going to check is, first, is log expression isolated on the left side? Is it the only log on the left side? Yes. There's only one log expression here, and that is set equal to 3. So we're ready to rewrite this. So rewrite this in exponential form. What is the base? Base is 2. And the exponent is going to be 3. And we're going to bring down that argument of 3x minus 4 as the other side of the equal sign. Now let's solve this. Now this is going to be a very easy equation to solve. But then just seeing that you need to rewrite this log expression to an exponential equation before you add 4 or divide by 3, that's going to be the important step. Okay? So you know what? I will even write it. Step 1, what did we do? Rewrite. Oh, I should say step 1. Step 1, rewrite in exponential form. And sometimes that may not be the first step. Sometimes the first step is to kind of move all the logs to the left side and combine them using the properties. But this one, the log was already isolated. So our first step was just to rewrite this in an exponential form. Now let's solve this. 2 to the third power. That's going to be 8. We have 3x minus 4. And now we're just solving a linear equation. Add 4 to both sides, we get 12 equals 3x. If you divide both sides by 3, you get x equals 4. Now, just gonna keep on checking my solutions because I want to make sure that is the real solution. So check. What is log base 2 of 3 times 4 minus 4? Is that really equal to 3? That's what we're checking here, right? That's log base 2 of 12 minus 4, is that really equal to 3? Log base 2 of 8, is that really equal to 3? And that is true, right? Because 2 to the third power is 8. But, you know, you can go ahead and plug it into the calculator, see what this gives you on the calculator, and see if that's really 3. And that's going to come out to be true. Now, all of these just came out to be good answers, but I want to show you one of them. We'll see that one of them that the check actually finds out, oh, it's really not a solution. So then we're going to have to just cross out the solution. But let's keep going. Let's solve a couple more. Now, this one's a little different. At least the log is isolated and all by itself on the left side of the equation. But what's the base? Because we may ask that question. We need to rewrite this in an exponential form. What is the base? And base for a common log. This is a common log, right? Is going to be 10. It doesn't say it, but it is 10. 10 to the what power? 10 squared equals negative 12x plus 4. Alrighty, we're ready to solve this. 10 squared is 100. We got negative 12x plus 4. Let's solve that. Subtract 4 from both sides. You get 96 equals negative 12x. If you divide both sides by 12, let me get a help from my tiny little calculator. What is 96 divided by negative 12? I got 8. Negative 8. So I got my solution to be negative 8. And what we can do is we can check it. Of course we should check it because we want to make sure x equals 8 is the real solution here. So what is log of negative 12 times negative 8 plus 4? Will that really come out to be 2? We can check that. Negative 12 times negative 8 plus, I forgot, plus 4. Okay. Regular common log, negative 12 times negative 8 plus 4. And if I hit enter, I got 2. And wasn't that number to the right side of it? Yes. So the check worked. We know this is the solution. Hope you're getting this, right? It's not that bad. It looks so intimidating because we were new to this log expression. But we know exactly how to rewrite it because you completed that quizzes assignment for me. So we know how to solve it. Now. It looks like the log expression was almost isolated, but there is something in front of it, isn't there? Well, there's a 3 in front of it. So what you're going to do before you start is first divide both sides by 3. Then you will have natural log of 5x equals 4. Now, another good question to ask is this. What is the base? What is the base here? Because, guys, we're looking at a natural log. This is a natural log. And we're going to need to know what the base is if you want to rewrite this in exponential form. And the base is going to be e to the 4th power equals what? 5x. Now, this is a good one for me to show what I mean by I want the exact form. Divide both sides by 5. That's how you will solve for x, right? So I will ask you to write the exact form is e to the 4th power divided by 5. And let's get the decimal approximation. And what's the decimal of that going to be? And we're gonna just round to 4 decimal places. And that's, I think I usually want it that way on the exams. So what you're gonna do here is when you got the exact form already, the final answer is e to the 4th divided by 5. But I want you to type that in the calculator. And you know, I got an app, but there's gotta be like a scientific calculator. And I did find it. It's Google search scientific calculator, and I really like this one, scientific calculator by Desmos. I'm gonna go and type the e to the 4th power. Where do I go back? Not the equal sign. E to the 4th power, and then I will divide that by what was the number? 5. E to the 4th power divided by 5. So if you don't have your scientific calculator with you, I found an app online or Desmos scientific calculator that got me that the decimal approximation is 10.9196. 10.9196. So that's what I mean by, let me write it down first, 10.9196. That's what I mean by I want the exact form before you type that in the calculator, and the decimal approximation rounded to 4 decimal places. So I want you to do that when you're doing the daily problems. Now this one's going to be very similar to what you will do on one of those 3.5 problems. But let's do one more. Let's do another logarithmic equation, or the natural log equation. Sorry about that. It got flipped. All right, let's solve this. Now, the previous one, we divided by, 3 to start the problem, but we're not going to divide by 4 here. You see the 4 is positive, so to cancel out that positive 4, I'm going to subtract 4 from both sides. Then I will get natural log of x plus 5 equals what number? 4. Now, we're going to rewrite this in exponential form. So the question is, what is the base? And you know, if it's natural log, the base is e. E to the 4th power equals x plus 5, right? Now, are you going to divide both sides by 5? No, you're not, right? You're going to subtract both sides by 5, right? You're going to subtract 5 from both sides. So here we go. Let me go ahead and write the exact answer. X equals e to the 4th power minus 5. But that minus 5, we're not subtracting the 5 from 4. We're subtracting 5 from e to the 4th power. So what we just found, this is the exact form. I want you to please, because I know you're listening to me, I know you're watching these lesson videos to complete these assignments, make sure you write the exact form and the decimal approximation. If somebody turns in the work, just the decimal, no work, no exact form, I'm going to just send it back and you're going to wonder why. All right, now let's get the decimal. Decimal. E to the 4th minus 5. I'm going to go over here and do e to the 4th power minus 5. So that one is kind of similar to what we did before, but we're not dividing by 5. We're just subtracting 5. The answer is 49.5982. 49.5982. 49.5982. So this is the decimal answer, but I also want the exact form when you submit your classwork. So that was half of the log equations. We're going to do a couple more log equations where you will have to actually combine some of these logs. So let's look at some of the more challenging ones on page 2. After going over these 4 problems on page 2, I will stop. And I will ask you to, as a quick break, try the 3.5 problems number 1 and possibly 5. 5 is going to be the hardest one, but we will come back. I will come back and start another video where I teach you how to solve exponential equations. So after the page 1 and 2, you should be able to try number 1 and 5. Okay? All right, let me go back to page 2 now. Now this page 2, there's some easy cases, even though you have logs on both sides. And now these are the cases where we have to really check the answers. And I think I was being bad and forgot to check the answers on the last 2 equations. But now, when you have logs on both sides, those are the ones that you really want to check the answers, okay? Now, let's take a look. If you have log base, if you have log base 3, and I have x in there for the argument, and I say, hey, I have log base 3 of 5. Without really solving the log equation, can you see by just their position, x must be equal to what? X must be equal to 5, right? Because if they're the exact same everywhere else. So that's what the equivalence property of logarithmic expressions in this purple box is saying. And sometimes it's as easy as that. Now, if you take a look at the first one, I got log base 2 of 3x minus 7 equals log base 2 of 8x minus 2. Notice they're exactly the same. I don't want to say we're canceling out these log base 2's, but what you can say is just, if they are exactly the same, the arguments must be exactly the same. So what you can do is just grab these 2 and set them equal to each other, and we will solve that. I'll subtract 8x from both sides. I will get negative 5x minus 7 equals negative 2. Let's add 7 to both sides. We get negative 5x equals what? Negative 5. oopsies, no, not -5, +5. If I divide that by -5, I will get x equals -1. Okay, so that's going to be, well, here's the thing though. I don't know if that's the solution just yet. So what I'm going to do is I'm going to go ahead and plug this back in and see if that's really the solution. So let's be good about checking solutions again. Check. I'm going to see what is log base 2 of 3 times -1 minus 7. And see if that's really equal to log base 2 of 8 times -1 minus 2, okay? The left side is going to be log base 2, -3 minus 7. And the right side that we're trying to see if they're really true is log base 2 times -8 minus 2. Now, I want to keep on going, and you'll see. And you may say, oh, they're the same. But I'm going to show you something, okay? The argument both came out to be -10. So you may think, oh, that's fine. We're fine. But, if you remember something about the domain of a logarithmic function, how did you set up the equation when I asked you to find the domain of a logarithmic equation or function? You did. Argument must be greater than or equal to 0. So what I'm going to show you is this. I'm going to go ahead and type this in my calculator, log base 2, -10, and show you that this is actually undefined. So log base 2 on my Desmos, I'll go ahead and say log base. Where are you, log base? Do they have log base here in this calculator? Oh, I don't see it. Maybe if I just type this in, log, will they be able to tell me log? Oh, maybe they will have it. And then usually I press like, what can I do? How do I make this the base? You know what? Unfortunately, I don't know how to use the log base function in this Desmos calculator. So I'm going to have to go back to the app that I downloaded. And before I go there, let me look at this one more time. 2 as the base and -10 as the arguments. So take a look. I'm doing log base 2. And then what was the argument? -10. Now watch very carefully. If I hit enter. Oh, no, it worked. Oh, it worked. Oh, no, it didn't. It didn't work. Okay. Take a look. What do they have at the end? I wish I can point it there. We're looking for real solutions, okay? Now, this is frustrating. What if you type this in your TI-84 calculator? Will you please do that for me and let me know? On your TI-84, type in math. Go to log base. And type in log base 2 -10. I never used this app before this semester, but, well, now they wanted to actually give me an answer, so they gave me an imaginary, but we're looking for a real solution. So what we're going to say here is that -1, it's called an extraneous solution because it's really not a real solution. Because if x is -1, the arguments turn into negative, right? Arguments turns into -10 on both sides. And the domain of a logarithmic function, the argument better be greater than 0. So we're going to say this is not real. This is not real. And it kind of sucked that my app actually tried very hard to find me the imaginary solution. But I want you to try to type this in your handheld TI-84, and it should say error or not real, so that we can go ahead and say this is extraneous solution. Basically, whatever that makes the argument negative, that's going to be an extraneous solution, okay? Even though it does make it look the same on the left and the right side. So that's why I kind of wanted to, keep on talking about checking your answer, because you will see a couple of these cases, okay? So what would we say? Do we have a solution in number 1? No, not real solution. We just have an extraneous solution. All right, let's try another one. I may have to get a new calculator app, guys, because I want the one that says, oh, it's not real. All right. Now this one, oh my goodness, take a look very carefully. We have logs everywhere. We have logs on the left, logs on the right. But well, no, remember what we said. We want to combine all the logs. But what I can do is, let me go ahead and go over or simplify these two first. Using what property? The quotient property. Notice these are the same common logs connected by a minus sign. So what I can do is I can rewrite this as log of a quotient, x plus 6 divided by what number? 3. And I can say that equals the right side, log base, well, common log of x. Notice that we can now set these arguments equal to each other. Okay, so say x plus 6 over 3 equals x. And we can solve this by first multiplying both sides by 3. Then you will get x plus 6 equals 3x. Subtract x from both sides, you get 6 equals 2x. Therefore, x comes out to be 3. Now, I circled it, but you know what to do. We better double check and see if that's the real solution by plugging this into the function or to the original equation. So here's my check, okay? Let me make this a little bit smaller so that I can do the work over here. So check. Plug in 3 into the equation. Log 3 plus 6 minus log 3. Is that really equal to log of 3? Well, let me go ahead and simplify as far as I can. Log of what number? 9 minus log of 3. Is that really equal to log of 3? So that's what we're trying to check, right? And we use the quotient property, but let me type in log 9 minus log 3 on my calculator, okay? I'm kind of back to my, no, not this guy. Because I don't think that gives me what I want. So let me do this one. Log. Guys, there's something wrong with my memory. I can't remember anything. Log 9 minus log 3. If I do that, I got that decimal. And the right side was simply log 3, right? If I type it, I get the exact same decimal. So we know this one checks. So this is okay. Checked. So x equals 3 is a good solution. We're going to keep that. We don't call that extraneous solution. It passed our check. All right, I got 2 more to go over with you. Now, this one we had to use what? We had to use the quotient property. But you'll see we will use more and more properties that we talked about in section 3.4, okay? All right, let's go down. If I can. What's going on? My app kind of stopped. Uh-oh, hello. Let me go back out and try to go back in. Okay, now that worked. Thank goodness. All right, I got 2 more to go over with you, and then we'll take a quick break trying these 2 problems on the other side. Now, what I'm going to do is I'm going to circle all the log expressions because I want them on the same side, right? Notice that I got a log of log base 5 of x plus 2 on the left side, but that guy was on the right side. So let me move that over to the other side. Log base 5 of x plus 2. Now, that was a minus, so I'm really adding log base 5 of x plus 6 to the left side, to both sides, and that's going to equal to the only number that's left is 1. Now, we're going to combine these 2 together. Notice they're common base logs, and they're connected by a plus sign. So what rule are we using? We're using the product rule. So log base 5 of x plus 2 times x plus 6, and now that equals what number? 1. Let's FOIL this. Log base 5 of x squared plus 8x plus 12 equals 1. I FOILed and simplified the middle terms. I know you can do that. All right, let's rewrite this in exponential form. If you rewrite this in exponential form, the question is, what is the base? The base is 5. The power is 1. 5 to the first power equals x squared plus 8x plus 12. Subtract 5 from both sides so that we can have a quadratic form. X squared plus 8x plus 7, right? And look, thank goodness, this is factorable. I'm so happy. We can say x plus 7 times x plus 1 is the factor form. So we got that x equals -7 and -1 are, I should say, potential solutions for right now. Because take a look, we gotta check these two answers separately. I'm going to go ahead and plug in these answers into the original equation and show you that one of them is actually not a real solution. It's going to be an extraneous solution. So here's my check. Just going to plug it into the left side. Log base x plus 2, right? I'm going to do -7 plus 2. If I do that, I get log base 5 of what number? -5. Now, notice the argument came out to be negative. This came out to be negative. And that's a no-no, right? A domain of a logarithmic function, we must have a positive argument. Therefore, this one, x equals 7, this one is an extraneous solution. Now, let me check the other guy. What about log base 5 of -1 plus 2? Now, that comes out to be log base 5 of +1. So that one's okay. And if you plug in, and we can do that part in our head. If you plug in -1 in there, that side will also give you a +5 for the argument, right? So that one's also going to be okay. So now checking part really, it makes it, the reason that I'm doing checking is because I want to make sure that the domain is, the solution is in the domain of these logarithmic functions. But it's also a good idea to check the solution just to see if the left side really equals the right side. But I need you to check your solutions, okay? So one more. And then I think you're ready to try some of these log problems on your own, okay? All right, the last one, number 4 on page 2. What are we going to do here? Now, what I noticed is that we got log expression on the left side, log base 2 of x minus 9. And I got another log expression on the right side. So what I need to do is I need to move this. I need to make sure that all the log expressions are on the same side. So I'll say log base 2 of x minus 9. And this was a positive term over here, right? So you have to subtract log base 2 of x minus 2, and the only thing that's left on the right side is simply 3. Now, what property are we going to use? That's subtracting, so we're going to use the quotient rule, or quotient property. So write down log base 2 of x minus 9 over what? X minus 2, and that equals 3. Now let's solve this. Well, in order for us to solve something that's in this form, we're going to have to now rewrite this in exponential form. So the base is what? 2. Power is 3. So 2 to the third power comes out to be x minus 9 over x minus 2. So 8 equals x minus 9 over x minus 2. To solve for x, let's go ahead and multiply both sides by the denominator of x minus 2. If I do that, I will get the denominators over there canceled out. And if I distribute, I will get 8x minus 16 equals x minus 9, right? Let's solve this. Subtract x from both sides. I get 7x minus 16 equals -9. Add 16 to both sides. 7x equals 7. Hooray! So therefore, what's x then? We got that x is... x comes out to be 1. Now, we need to check if this answer is a real solution, right? Because you remember, we always have to check the solutions when we're solving these log expressions. So, what I'm going to do is I'm going to plug in 1 into the original equation. So, check part. Let me use a different color. So, here's my check. Log base 2 of x minus 9 now turns into 1 minus 9. And I go, uh-oh, right? Because why? 1 minus 9 is -9. Well, that's the negative. This is negative. So what does that say? The only solution that we got is an extraneous solution because this is an extraneous solution because we got to make sure that the argument comes out to be positive because that's what the domain of a logarithmic function is, right? So if this happens, do we really have a solution? No, we have no solution. So we did very hard work, but we ended up finding that this equation has no solution. So you may have to, you will have to, I ask you to please check your work all the time when you're solving these log expressions, log equations. So that was it for just a couple examples of solving logarithmic equations. What I want you to try now is try number 1 and number 5 on the 3.5 problems. 1 is similar to the ones that we went over on page 1, and 5, that one is similar to, but here's the thing though, when you're solving number 5, I would, if I were you, I would add that expression to both sides and rewrite it as 3 equals log base 3 of x minus 6 plus log base 3 of x. And then I will use the product rule to combine the right side instead of subtracting, and so I think that will be the easier way. But I want you to try number 1 and number 5, and then when you're done with them,